A modified version of the Surf Lifesaving Ironman consists of 3 events. A competitor will run along a straight beach from point F to point A, which is in blue, and then the competitor swims around a buoy at point B and back to the point F. From there, the competitor runs along the straight beach again, this time from F to D, and then collects a board and paddles around a buoy at point E, and finishes the race when they arrive back at the point F. And we have the diagram shown below, and we annotated it with the blue legs to represent the run, the red to do the swim, and green for the paddleboard. It turns out that the point F can be moved anywhere between the points A and D, and we're going to let X be the distance in meters between points A and F. So from the animation we can see that as the point F changes, the lengths of the swim and the board run change. So that is, the hypotenuses of those triangles are changed, along with one of the lengths of the sides of the triangles. So overall we'll have different lengths for the overall competition depending on where we select the point F to be. For part A, we're asked to find, in terms of X, an expression for d of X, which represents the total distance of the Ironman race. So d of X, which is going to represent the distance, is just the sum of all of those lengths. So if we start off with the run leg, it's a total of 60 meters no matter what. So we're going to have 60. And then we need to add on to that the length of the swim, which has a fixed 20 meter length along with this hypotenuse. And that hypotenuse changes depending on X down the bottom. So we know that this is a right angled triangle, so this length here is going to be the square root of the 2 side lengths as squares added together. So we're going to have X squared plus 20 squared. So we need to add that onto our distance calculation, which is X squared plus 20 squared. And then we'd need to add on the last leg, which is the paddleboard, and it has a fixed length of 30 plus the hypotenuse, which will change depending on X. So if this length was X, we have this length here would be 60 minus X, which means the distance of this hypotenuse would be 60 minus X squared plus 30 squared. So that's the last thing we'll add on here. So therefore, our distance expression, d of x, can be simplified slightly. So the 60, the 20, and the 30 can be combined to give 110. And then we'd still have plus the square root of x squared plus 20 squared, which is x squared plus 400, plus the square root of, and here we would have 60 minus x squared plus, and 30 squared is 900. So that is the expression for d of x, which describes the distance, or how the distance changes for this Ironman race, depending where x, or the point F, is starting at. For part B, we're asked to determine the location of the point F, such that the distance of the Ironman race is a minimum, and we're asked to state this minimum distance. On the CAS calculator, go into the main menu. And the first thing we're going to do here is actually enter in the expression we found in part A. So that was 110 plus, and then using the keyboard we had the square root of, and it was x squared plus 20 squared, which is 400. And then we add on to that the square root of, and it was 60 subtract x squared plus 30 squared, which is 900. So what we're actually going to do with that is we're going to define it. So we're going to go interactive define, and when we want a different function name other than f, we need to use the ABC keyboard. So we're going to use the lowercase d here, so d of x is our expression. And now we could do the rest of this question without a graph, but it's sometimes nice to get a feeling for what's going on. So I'm going to click the graph button up here, and that brings up the graph screen where I can drag down just d of x and it will sketch the graph. And we can't actually see any of the graph at the moment, but that's just because we need to change the view screen using these 4 arrows to better see the graph. So we knew that x moved between 0 and 60. That's the values that x could take on in our question. And the y values, we know that the minimum distance is going to be at least 110, but obviously a bit more. So I'm going to try putting 150 in here. And the maximum distance is a little bit hard to know, but you could just make an educated guess or put a number bigger than 150 in there and see how you go. So I'm going to try 250 and hit OK. And that gives us a reasonable view of the distance function. And on the graph, we can see that there appears to be a minimum point somewhere. So we can go analysis gsolve min, and that will find the minimum value, but it gives it as a decimal, so that won't be quite what we need for this question, but I'll just leave it there for now. If I go analysis gsolve max, nothing will be found, but we could use fmax instead. So analysis gsolve and using fmax should give us the maximum occurring at 60, and I'm just going to lock that coordinate there. So they're obviously not exact, so we're going to need to use the main screen again to find those exact values. So for this part of the question, we want to drag d of x down, and we want to go interactive, calculation, fmin, fmax, and to find the minimized distance, we use fmin. And we know that the domain was between 0 and 60, so they're the x values that make sense for this rule or are included for the question that we're given. And hitting OK gives us the exact value of the minimum total distance, as well as the x value for which that occurs. So using fmin on the calculator, we found out all the information we needed, but in a question you might need to put some working steps down. So for this question, as the minimum was at a turning point, our working for this question would be that we set the derivative d dashed of x equal to 0. So therefore we found that x was equal to 24. So this can help to answer the first part of the question. So that was determining the location of the point F. So with that in mind, F should be located 24 meters from the point A. And that minimized distance we could find by doing the d function evaluated when x is 24. And from the calculator, that was 10 root 61 plus 110, and that is in meters. So now we have where F should be located, along with the minimum distance that's possible for this Ironman race. For part C, it asks us to determine the location of the point F such that the distance of the Ironman race is a maximum, and to state the maximum distance. Now we're being asked to find the maximum total distance of the course, so we're going to drag d of x down, and this time we're going to highlight and use interactive calculation fmax to find the maximum total distance. And we're going to go between 0 and 60 for our domain. So hitting OK will give the maximum possible course value, as well as the x value where that occurs. And again, we have to use the main screen because we only get decimal approximations out of the graph screen. So from the calculator, we know that the maximum possible distance for this race occurs when x is equal to 60. So with that in mind, we can now describe the location of the point F. So whereas the minimum that we discussed in part B was at a stationary point, this is an example of an absolute maximum, where our maximum value isn't found using calculus, but by evaluating one of our endpoints. So to find that maximum distance, we could evaluate the distance function when x is 60, and we find that that is equal to 20 times the square root of 10 plus 140 meters. So now we've found the location of the point F, and we've also been able to state the maximum distance of this course. So we know that F should be located 60 meters from the point A to maximize the total distance of the Ironman race, or essentially that means that F should be at the point D on the diagram. And we know that the maximum possible distance of the course is 20 root 10 plus 140 meters.